So thank our organizers for inviting me to speak to you today. So my plan for today is to talk about a bit of my journey, because I was sitting alone here, so I didn't get anyone to talk to. But where I come from is really thinking through this shift from information technology, that we think in terms of the technology as sending bits and information theory, and think through about, well, if we were to think in terms of human experiential phenomenon, how would we approach that, and how we can communicate that? And how would that change the way we think about the underlying infrastructure? I found it very interesting to see the future topics that were listed there. And in some sense, maybe I'm a little concerned because the ones that I'm talking about today were not necessarily listed on there. So I'm not sure what that means. But the ones listed were very much information push topics, and not so much thinking through what the future for people is going to look like. So I'll try and bring that perspective into play, and I will try to keep it within a reasonable time frame. So, so I'm looking towards what the future communication is going to look like, and it's this shift of my thinking from IT to what I call ET, which is not go home, but ET. Experiential or experience technology. So that's where I'm coming at this from. So I'm going to show you a few things. My own lab, the Human Communication Technologies Lab, I started that at UBC back in, it's a little embarrassing, but 1998. So it's quite a while now. And then before that, I was in Japan working on these topics at ATR. And before that, in virtual technologies in California, I did some work in the startup world down there, and then coming out of University of Toronto in machine learning. So that's really my background originally in machine learning. But as you'll see, some of the directions I did in the past really led me to where I am today. So the things I'm going to talk about are the body and the expressive body, and how we might transform what our capacities for expression look like. Talk about one of the principles I argue for, that the next major wave in terms of media is moving video to be a first-class citizen of media. So what's that going to take to make that happen? And I know we're seeing things like TikTok already, and those are starting points of this shift that's starting to happen. So I'm going to argue for what it's going to take. And then some work on 3D displays that we're doing, which relates to this online presence and communication in the online setting, which, because of the pandemic, is really accelerated. So hopefully it'll have some bearing. But let me start with, and this is super old work, but it really brings together many of the things I'm going to talk about today. So this is called the Glove Talk 2 system, which I did back way when. Oh, I should maybe say a little bit before I start that. Whoops. So what you're going to see is a person speaking with his hands, where the gestures are transformed through a neural network into underlying frequencies and amplitudes of speech, of a speech synthesizer. And the synthesizers take those frequencies and amplitudes and play them. And with enough practice, he was able to learn to speak, in this case, English, but it's really at the vocal tract level. So he can speak other languages with this. There's nothing special about English in this. And the neural networks are just there to make the task easier, because it's a very hard task. In his mind, he's thinking like a vocal tract that he's manipulating. The neural networks are mapping that mental model of his and his gesture into the sounds of a vocal tract. So that's what you're going to hear. There's a lot of, he's got a glove on both hands and a foot pedal, all being sensed and mapped. All right, let's try and play this. Should have audio coming shortly.
I am Sam. I am Sam. Sam I am. That Sam I am. That Sam I am. I do not like that Sam I am. Would you like green eggs and ham? I do not like them, Sam I am. I do not like green eggs and ham. Would you like them here or there? I do not like them here or there. I would not like them anywhere. I do not like green eggs and ham. I do not like them, Sam I am. Would you like them in a house? Would you like them with a mouse? I do not like them in a house. I do not like them with a mouse. I do not like them here or there. I do not like them anywhere. I do not like green eggs and ham. I do not like them, Sam I am.
Okay, so that's him learning to speak with that.
Could you keep the mic a bit closer to your face?
Okay,
Yeah.
there it is. I'll just talk with my hands, actually. That'll be easier. So that's him speaking. It's quite robotic sounding because he's doing direct control of formants and amplitudes. On the other hand, it's surprisingly expressive. He has control of pitch, and he can make those super segmental sounds that he learned to do on his own with the mapping, the neural network mapping in between. So that work way back when, in an effort to say, well, what's going on there? Why is he able to be expressive? Most of these types of systems which do recognition of gesture into words or letters or something like that, you can communicate the information, but they're not very expressive. On the other hand, it's kind of robotic sounding. It's not very natural. So that led me to really pursue 25 years and still going on how to make that sound more natural. It still took him 100 hours to learn. He speaks with his own vocal tract normally, so he didn't have to learn a language or anything. But to learn the gestural space took him 100 hours, even with the machine learning in there. So how can you make that easier? And the more fundamental question, which is, he's able to speak English in this case with his hands. Well, that's a mapping from his representation of speech in his brain, which would normally go to his vocal tract, to a whole nother set of muscle groups. And he was able to learn that in 100 hours. Well, what's going on up here? Like, how is speech being represented such that he can control amplitudes and frequencies, not words or, not a language model, but actually a sound model? It's much more like playing a musical instrument. So he's learning to play a voice instrument, and the music is not music, it's language. So how is that being represented in the brain? If we could figure that out, we might have different pathways for understanding, say, speech, like natural language understanding, speech recognition, and voice, as well as prosody and expressive components. So that's been the pathway I've been going down. So first step was, well, one of the things that's underlying the model that he's working on is a frequency and amplitude space, formants in this case. That's not what the brain typically represents. We work in muscles. We control the muscles of our vocal tracts. So to investigate this further, I have been working on an articulatory synthesizer such that I can map either brain or gesture into muscles, synthetic muscles. So that's an articulatory speech synthesis. So we've been working on this thing called ArtiSynth, which is a biomechanical modeling toolkit that allows you to do tightly coupled rigid body mechanics with continuum methods, finite element methods, and have them work well together, because soft tissue, biological tissue, and rigid tissue like bones, if you do them all in FEM in continuum, it's extremely slow, and we need this to run in real time. If you do it in articulated bodies, then you don't get the types of phenomenon that happen when your tongue, say, hits your palate, like a d sound or something like that. So we built this thing because that doesn't exist. It's called artisant.org, which is free to download. And so it kind of has these elements, which then we can make into biological models. And then from the biological models, we can then get function. So in this case, it's speech. It also does chewing and swallowing and breathing explorations. But for my purpose, speech is really where I want to go. So being able to take the biomechanics here and translate them into speech. So that's an aeroacoustics problem. That should be switching. So just to give you an idea of some of these, this is a human model that we created called Frank for Frankenstein, because it really is a piecing together of models from various different people to make a complete biomechanical model of a head. Yeah, so you can see there it has tongue and different fidelity models. So the tongue is a finite element model, whereas some of the rigid bodies are spring mass type models, point-to-point muscles, and they all play nicely together in this framework, which is really a big part of what we built. So there's a vocal tract that sits inside. As the muscles articulate, then the airway changes shape, and then we do the aeroacoustics through that. That's just some vocal fold models, so you can see the vocal folds moving. Soft palate, so for different types of sounds, like nasal sounds, that thing opens up. Yeah. Whenever modeling biological tissue, I used to say, oh, we should start with that. That'll be a lot easier than, say, the tongue. No, they're all hard. Doesn't matter which one. They all have their complexity to them. So anyway, you get a sense of what that's looking like. So once we have those biomechanics, now the muscles, these simulated muscles, activate, moves the airway, and then from the airway, we do the aeroacoustics. So 3D aeroacoustics with finite element methods, for example, are extremely slow. For us to do even like, fractions of a second, like 100 milliseconds worth of speech synthesis in 3D can take days and days of computation. Obviously, that's a place for machine learning to investigate, which I'd be happy to talk about that as a domain. An alternative that we're currently looking at, because it runs in real time, is looking at a 2.5D model of that and doing real-time wave propagation through the vocal tract itself of the acoustic pressure wave. So that's your favorite acoustic pressure wave, just to know what's going on there. It's all been implemented on the GPU to get it to run in real time. Just to remind you of what these things look like. So pressure, that's what reaches your ear and causes the sound. And it's moving at some velocity. And there's an excitation. In the case of the vocal tract, your vocal folds start to vibrate and cause energy to enter the system, and that's being shaped by the tube, your vocal tract tube. That's an input. And then you've got walls, that's your vocal tract walls, and they can move and attenuate the pressure wave in varying ways. And that's what those equations are all, and speed of sound and density and stuff like that. And in the end, you get sound. That was supposed to be sound there. There it is. So that's just simulating in real time on a GPU using the textures to update those equations. And so you can see this little thing at the center there was just was injecting energy into the space. And then that would reflect off this wall. And you get a virtual microphone picking up that pressure wave, and that's what your ear would hear. So in a vocal tract, it might look like this. Here's a very simplified vocal tract. And so different shapes would make different sounds, and then the excitation, the thing that comes from your vocal tract, gets coupled to that. And that's a lot of the naturalness will come from that. So we're exploring that. Interesting is those same equations are also great for musical instruments. So we built a thing called a hyperdrum out of those same equations, because the drum head, when you tap on a drum head, that sound propagating into a two-dimensional, essentially a two-dimensional surface, and you get sound propagation there. And depending on the shape and material properties of the drum head, you get different timbres of sound. And so we built a little one where you could draw on a big touchscreen, draw different shapes of drums with different things. And that was a lot of fun. Same equations. So we're working on that. We've got a number of things done on that front. So how do you control this thing? So obviously gesture is one of the areas, and using machine learning to get it so that my hands can control those muscles. That's one thing. But we're also working because ultimately this is a brain-computer interface that we want to get. That is the representation of motor control of speech being translated into those synthetic muscle, right? Because now we have synthetic muscles controlling the sound wave. So that's so we're looking at ECOGs or electrocardiography, where you have actual sensors under the skull stuck onto the ventral sensory motor cortex in an array, and that those signals can then be used to map into the muscle activations. So we're looking at that. We've looked at EEG, and we were looking at MEG, but that's proving to be a challenge just due to the sensing problem there. There's also, as we start to look at including the biomechanics of speech into the pipeline, there's a connection with swallowing, and that how the biomechanics of swallowing interact with our ability to control speech. So that's led to a number of different phenomenon in terms of our understanding of vocal control and its relationship to speaking. So that's another project that's come out of that. Likewise, these biomechanical models are being used for virtual surgical planning, because obviously any modification of those things affects chewing and swallowing, breathing phenomenon, and so they can be used for those purposes as well, which we all do. From a future communications point of view, though, the thing that interests me is what's the brain doing in all this, right? What's your brain actually trying to accomplish when you're speaking? And we argue that the biomechanics of your vocal tract plays an important role in how your brain has structured its representation of speech, coupled with a language model. And, you know, a friend of mine once said, you know, why don't fish talk? Well, because they already know everything. They have nothing to say. They don't need to say it. So why do we talk, right? And our argument is, well, the only reason we're actually talking to each other is because there's a misunderstanding, and we're trying to communicate the meaning to the point where there's a mutual common understanding. In terms of information rate, that can be seen as we're trying to get the entropy, that is the mismatch in our understanding, to be as low as possible. Ultimately, if we know each other well, we don't need to say much more than, uh-huh. And that communicates everything we need to say. We don't need words. And that's minimizing that information load on your brain. So if your speech representation has been tailored to minimize the amount of information load to communicate to a coupled entity, another person, we do just enough until that entropy is low, so that we don't have to spend a lot of time on that. And that's what using your biomechanics can do. because when you speak, you can use your palate and just bang into, just move your tongue until it hits your palate. You don't have to have this super precise positioning, because precision requires information. If you don't need it, you don't want to use it. And so the biomechanics play an important role in that, incorporating that in our representations of language and voice. So if we want to create a brain-computer interface, we want to try and make the connection between brain signal to those muscle activations, optimize that channel so that there's minimum information load on the person with maximum information rate in terms of the exchange. So at the output, we want to maximize information throughput, input, minimize information load. And that's the criteria. And to do that, we argue that the representation of speech should incorporate the language model, the person that you're speaking to model, and the model of the vocal tract, the biomechanics. You put those all together. Ultimately, if we have a good model of that's predictive, we don't really need to say much more than, and we're understood. And if that's not understood, then we have to start clarifying and putting much more information in there. And that's sort of what I'm talking about in terms of experiential phenomenon. When we start thinking about communication as an experiential phenomenon, then we start thinking in terms of these other quantities of throughput, information throughput, and minimizing and maximizing entropies. So that's a big part of what we're doing. There's a nice diagram that kind of shows how that all gets incorporated into different models of voice and speech production. There'll be a test on this later. So we're looking at that chain of motor control for speech by minimizing those information requirements. So that a brain-computer interface is not sitting there trying to be a classifier into words or letters or something like that, text, but rather it's a transformation of a representation of meaning into these synthetic muscle controls to a listener that's providing cues about understanding, and that's what would be tuned. And then the machine learning is being used to optimize that channel. So that's what we're looking for. So that's a very large project I have going on right now that's exploring these things. So there's a big group of us working on that. So I argue this is, for our future communication, understanding these brain representations is going to be at the heart of reconstructing and pushing the technologies of our brains, whether it's virtual or augmented or many of the topics that were there. All right, so I'm trying to get through all these 25 years in 25 minutes. Okay, so that's that project. Another project that fits into the same notion of, well, what's our communication futures looking like? And for me, one big one is video representations. Really did come out of thinking through that speech is not just an audio phenomenon. Yes, you can listen to somebody over the phone, if anybody remembers what that is, and understand them. But the visual signal provides much more information. And in fact, if you have to choose between visual communication, like what you hear is visual or auditory, your brain will prefer the visual signal. It'll tend to believe the visual more than it believes the audio. So if you hear a sound that says one thing, but you see the person saying another thing, you'll believe what you see, not what you hear, which is kind of interesting. So my argument is the challenge with video as a communication medium is that we're still somewhat stuck in the producer-consumer model of what video actually is. And so, so it's very hard to author. It takes a lot of effort, and that's a fairly significant barrier as a communication medium. Unlike text, we learn as children how to read and write. And so that writing process is a hard process, but you learn it at an early age, and there's lots of tools to help us. So that authoring makes, for video, I argue we want mutable video, so that when you get a video, just like think of yourselves when you get a Word document, you get a video somebody sends you, in Word, or Google Doc for example, you just change it. You don't even think about it. You know, if it's a PDF document, you get kind of annoyed that you can't change it. But the other, normally you just change it. Don't even think about it, send it back. But video, that's not true. The mental model of video is not like, hey, I got this material that I can adjust and change and send it back. So it's not mutable in terms of that. And the technology to support mutable video is lacking. The other one, it's hard to integrate. So if you do a cut and copy paste from your video into your Excel spreadsheet, what does it do? That's a weird question, right? But when you take a text and copy and paste it, it does something. It might bring up a little dialog box, say, well, I don't exactly know what that text is all about. Can you help me? You know, is there commas or spaces or whatever? It tries to give you a little help to tell you how it's going to integrate well with a spreadsheet format. But for video, we don't really think about, well, how would I copy paste video into the other media? Likewise, if I copy paste text into my video, what should it do? Well, if it was a script, right? If you copy paste a script from your text into video, well, there should be little synthetic actors that play the parts, make the video, for example, or other forms of text that can be understood and represented, likewise video to text. There's different ways of talking about that. So that's interoperable. And then the last is the bidirectionality of it. So that is, we converse exclusively in video, right? So I send you a video and you respond with a video in the mental model of video as a first-class citizen. You think video, just like you think text. So we've been working with these three principles to explore how those will have impacts on some of the things we do. One of the big things, given we're in a university, is looking in the educational context. So a thing called vidX, which we let loose on a pile of different classes and students to allow them to do annotation of that video and start to integrate some flavor of text. Also talking about video, different ways to reference. Like when video, you might say, hey, look at that. Well, what's that refer to? Well, that's something in the video. And when people comment about video, they're commenting about parts, and anyway, integrating that. And as well as, again, paper notes, so text with video integration. So that's been part of what we've done. So I have a little video here that just shows some examples of it. But here would be this vidX viewer for education, and it integrates things like the transcript of what people say with annotation and various crowdsourcing statistics that all get integrated together in a learning environment. I'm not going to show too much of that video because I don't want to run out of time, but you get the idea of you can seamlessly move between the video representation and the textual representation. And you can even select intervals. We don't call them clips because for many cameras in our future, they never turn off. You turn them on, they never turn on. There's no beginning or end. There's just intervals between them, within that. Notebooks, that's big education thing. People are still using notebooks as the center of their learning ecology, and so it should play well with notebooks, with written notes. So we explored some video, computer vision methods to get the notes in and then link them to what you were watching at the time. So essentially visual search in video space for the lectures that were happening while you're taking notes. That's another problem with video, or challenge with video. Page numbers, right? We don't have page numbers, and it's very hard to make an index. So these are analogies to text that don't map so well. So we have time intervals, beginning and end, but those are very difficult for referencing. So how do we get page numbering for videos? So that was, again, this idea of indexing. So we explored that. Referencing in videos, so we did a big project on that. And this is a proof of concept thing where you could actually select parts. And then when people comment on them, these are little smart links that can either link to the video, the audio, or other parts of the video. And as you're commenting and you just hover over those things you see in line in the comment, you don't have to scroll up to the top and look for the thing. No, it shows up within the context of the conversation. And we just showed that that was very, very effective. So you can move around in your commenting, and the videos are embedded as part of that. So I can encapsulate this of, we spent enormous amounts of time and energy on text. So I would argue our future for communication through video requires a rethink in terms of the equivalent of the pencil and paper for video. What does it actually mean to write video, and what does it mean to read video? It's not about viewing or watching or consuming it. And likewise, it's not about authoring or composing. It's about writing in video. And that means genres, structure, templates. And you see flavors of this. Canvas, for example, with lots of structure, TikToks. So we're seeing this emerging, but I say let's embrace it 100%, and you'll see all sorts of new exciting things for ways people can communicate. So this is our group here. And then our last topic, do I have time for our last topic? All right. Is around this virtual reality challenge and creating experience in this with virtual entities, like things in the digital space, and bringing them into our real space. I know virtual reality is putting you into that virtual space, and that's another important area too. But I'm talking about how do you bring that virtual space into your space. And for teleconferencing, which is where we're working on right this moment, the challenge we have, and we have a virtual conference today with people on board, simple things like eye contact. Like I can look at people here. They're not going to be, I can't have eye contact them with easily, right? They don't have, their screens don't have the ability to take me and put them in their space, or take them and put them in our space, in our real space. So we've been working on technologies to achieve that. So this crystal display, a spherical display, is the thing we've come up with. So it's a spherical display with a bunch of projectors underneath. They come in different sizes, and it's view dependent. So as you move around the thing, the rendering adjusts. It's like a one-person hologram. So I guess we can do 2 up to 4 people. So, but you know, a small number of person hologram where the perspective is rendered as you move around. And so you get motion parallax plus stereo. Though you can, it still works with motion parallax, even if you don't have stereo, it just doesn't work as well. So that's the display. So now that, and we've done lots of studies that show it's very realistic, like things like size constancy is preserved in this type of display. And what size constancy means that if I see a person way over there on, say, on that roof, I don't think it's this little small person way over there. No, I think they're like a normal sized person just far away. And if they move closer, they don't get taller. No, it stays the same size. On my retina, it's just a very small number of, you know, when they're far away, it's hitting a very small part of my retina. And so my brain has size constancy and doesn't interpret that as a small person way over there. So that's size constancy. That's hard to achieve in virtual reality. Things don't look the same size as they do in real, and when they are changing depth, they look like they change size. So we got that display. It's situated in real world coordinates, so you get eye gaze somewhat for free as long as you're in a 1-to-1 ratio. We have technologies that can represent the human shape. and postures and movements, using machine learning for neural rendering, so we can have low, compact encodings of 3D representations of people that can support view-dependent rendering, right? Because you want the view to change for the receiver side. They're going to be moving around, so they need to see you. Like, let's imagine me right now. If there's this camera on me, the person on the remote side might be moving around me. So the remote side needs to have the ability to render in all dimensions, which you could do with a 3D model of a human, but that starts taking a lot of bandwidth. So the neural rendering approaches with automatic shape and motion capture can be used in that. And then the registration, which is really an AR type of problem, we have those methods as well. So we bring it all together. Oh, this was animated, I forgot that. Okay, well, doesn't add that much to be animated, but there you go. And so here's where we're at today. So we made this thing called the 3D Teleview or Open Teleview, because it's going to be released shortly. And this allows you to have, say, a sender on one side, receiver on the other. And this would be symmetric. We're just showing the one direction here, where there's a single camera taking an image of her, extracting 3D parameters of the speaker, and then compressing those into as just a 3D view, view agnostic representation. And then that gets transmitted across the channel. And on the other side, so now we have a low fidelity representation, 3D representation of the person. That gets reconstructed into a low fidelity version of her. And then we have a neural renderer that can take a pre-trained neural renderer on her image that can now take that low resolution image and resynthesize it as a photorealistic. So what you're going to see in this little video, what's happening here is a photorealistic rendering based on using a neural renderer that's been adjusted to run in real time with a few little technical details there. Runs in real time and is view dependent, right? So you put as an input into your neural renderer the viewpoint you want, coupled with the low res version that's come over the channel, and that reconstruction, the low res reconstruction. And that's all being synthesized here. So you'll see that kind of what it looks like here.
Hi, Bebe. How are you doing?
Hi, Cassia. I'm doing well. How are you doing today?
So that's a synthetic image. Yeah, so you can see some of the things that it does there. And just that's the little block diagram of what I just explained. So don't need to talk about that too much, but it is on the exam. So just details of what 3D head model we're using and some of the neural rendering techniques that we're doing. That's no longer in submission, that's been accepted. So just to summarize everything that about that project, we're really looking to get not so much our own technology, but actually get this 3D teleconferencing thing into the hands of researchers so that they don't just publish papers on public data sets and say, look how great it'll be for teleconferencing. It needs to be tested in situ. And so this research platform actually lets you plug and play different encoder and decoder technologies and different display technologies to actually run user studies, perceptual studies, to get those metrics that we're going to need to get 3D communication quality working well. So that's that project there. And there's the team all working on that. So just to summarize, my lab is really focused on this human experiential phenomenon and the underlying technologies that we can use to support that. And I'm arguing that for us who are looking at future technologies, that this is a pathway to really get at where the problems are in human communication that are not just technical problems. So it's a very multidisciplinary way of finding those problem spaces. And along the way, there's a lot of short-term, huge challenges that you can make contributions, but there's a long-term vision that, that's been part of civilization for a long time, that you'll get into that flow of that long-term path of research contributions. And again, I want to thank my team. We have a great, large team of people working on these topics. And various sponsors, Tri-Council, industry partners, which we're always looking for more, and various academic partners working with us as either visiting scholars or data sharing, these sorts of things. All right, well, thank you very much for your attention.
Thanks so much.